Hey everyone, welcome back to our AI series. In the last episode we looked at uninformed or blind search strategies like BFS, DFS, and iterative deepening. But as we saw, those methods don't really know anything about the problem. They blindly explore until they stumble upon the solution. Today, we're going one step further, into the world of informed search strategies, also called heuristic search. These strategies are smarter because they use extra knowledge to guide the search. Let's start simple. Imagine you're trying to reach a friend's house in a city you've never been to. If you just randomly try roads, that's uninformed search. But if you use Google Maps and follow the estimated distance or time, you're using informed search. That extra information, like the distance to the goal, is what we call a heuristic. In AI, a heuristic is basically a rule of thumb that estimates how close a state is to the goal. The first informed strategy we'll see is greedy best first search. This algorithm always expands the node that seems closest to the goal, based on the heuristic. For example, in route planning, it picks the city with the smallest straight line distance to the destination. Sounds great, right? But here's the catch. Greedy search is not always optimal. It may get stuck in local traps because it only looks at the heuristic and ignores the cost so far. Think of it like always chasing the road that looks shortest, but sometimes ending up on a dead end. Now comes the superstar of informed search, A-star search. A balances two things: the cost so far to reach a node, called GN, plus the estimated cost to reach the goal, called HN, so the evaluation function is Fn equals sign GN plus HN. This means A is both greedy and careful. It doesn't just look at the nearest goal but also considers the path cost already spent. If the heuristic is good, meaning it never overestimates, A is both complete and optimal. That's why it's widely used in navigation systems, robotics, and games like chess. Let's take the 8 puzzle problem as an example. We want to slide tiles into the right order. Two common heuristics are misplaced tiles. Count how many tiles are not in the right position. Manhattan distance. Add up how far each tile is from its goal position. Both are simple, but Manhattan distance is usually better because it gives a closer estimate of the actual moves needed. Good heuristics can drastically cut down the search space, turning an impossible problem into a manageable one. So, what makes a heuristic good? Admissibility. A heuristic is admissible if it never overestimates the true cost. For example, straight line distance is admissible because you can't fly shorter than a straight line. Consistency, or monotonicity. If moving from node A to B costs 5, then HA should be at most HB plus 5. This ensures A works correctly without revisiting nodes. If your heuristic is admissible and consistent, A becomes very powerful. Besides A and greedy, there are other strategies like hill climbing, keeps moving towards the best neighbor, but risks getting stuck on local maxima. Beam search, keeps only a limited number of best nodes at each level. Simulated annealing, uses randomness to escape local maxima. These are especially useful in large and complex spaces like scheduling or optimization problems. So to wrap up, informed search uses heuristics to guide problem solving. Greedy best first search is fast, but not always optimal. A search is the gold standard, complete, optimal, and efficient if the heuristic is good. Designing strong heuristics is the key to solving complex AI problems. In our next episode, we'll dive into game playing and adversarial search, where we'll see how AI systems make decisions when there's an opponent trying to stop them. If you found this helpful, don't forget to like, share, and subscribe. Let's keep learning AI together.